Hello everyone and welcome back to The Ways of Math. I'm your host Dan the Math Man, and today we're going to continue our series on the introduction to sets. Okay, so this is the second part of a multi-part series. If you haven't seen the first part, I strongly recommend you see the first part. We establish the basic definitions of a set and kind of get a feel for what a set is. Okay, in this video we're going to talk about set equality. So what does it mean for two sets to be equal? We're also going to talk about the cardinality of a set, and the cardinality is the number of elements that are in a set. We're going to describe what those are and how to find those. And we're also going to talk about the equivalence of sets. So what does it mean for two sets to be equivalent? Okay. Alrighty, so let's jump in. So the first thing we're going to talk about is set equality. So we begin with definition. Okay, mathematicians love definitions. If we don't have appropriate definitions, then nobody knows what they're talking about. Okay, so here we're going to define set equality. Okay, so in order to define set equality, we need to be talking about some sets. So suppose we have two sets. Okay, so suppose we have two sets, and we're going to call these sets A and B. Okay? Now we say in mathematics, A equals B, okay, which is denoted like this. So this is just saying A equals B, just like we would in the algebraic equation. Okay? But we say that A equals B if both sets, okay? So if both sets contain exactly the same elements. So exactly the same elements. Okay? Alrighty. So that means if every single element in A is exactly the same as every single element in B. Right? So if whatever is in A is the same thing as in B, that's what we talk about when we're talking about exactly the same elements. Okay? If the sets are not equal, well then, of course, it's very intuitive to suggest how we notate that. So A not equal to B, that's how this is read. So these are not equal. Of course, the converse or the contradiction of the statement. So if they don't contain. So this is does not equal. Oops. Does not equal. So we also denote if two sets are not equal by using this notation. So we say A does not equal B. Okay? So that's the notation. So this is the notation for A is equal to B. This is the notation for A does not equal B. Okay? So let's take a look at some examples. All right, so let's say we let A be the set, and we'll use roster form. Keep this fairly straightforward and to the point. So let's let A be the set 1, 2, 3. And suppose we define the set B as 2, 1, 3. Okay? Now keep in mind that in sets, so there's no specific ordering. We don't have to order or organize the elements within a set. Now, granted, we usually do, because as humans, we do like to have things ordered or organized, okay? But they don't have to be. And in fact, when you're dealing with chaotic or really messy numbers, there's kind of in some way no way to organize some sets. But just suffice it to say that it's not necessary that they have the same ordering. Okay? But notice that set A has exactly the same elements as B, right? So 1, 2, 3 over here. I have 1, 2, and 3 over here. Okay? So in this case, we would say that A equals B. So this would be true. Okay? Alrighty. Let's take a look at another example. Let's erase this, erase our definition so we can have more room for examples. Now suppose I define A in this way. So this is another example. There's going to be another set of examples here. Okay? So suppose I define A as 1, 2, 3. Okay? And then I use the same definition for B as I used in the previous example. Okay? 2, 1, 3. Okay? Now, one might have a tendency to say that these are equal, right? If you say them out loud, 1, 2, 3, 2, 1, 3, it sounds like they have the same elements. But be careful because we're actually describing the words are the elements 1, 2, 3. So these are words 1, 2, 3 versus these are numerals 1, 2, 3. Okay, so be very careful on context. And so you also want to be very careful on how you write things. So again, in mathematics, we want to be precise with how we write everything. Okay, if we're not precise, then we lead to ambiguity or possibly fallacy, which for those of you who aren't familiar with that, it just means it's something that's false. Okay, so in this case, generally speaking, we would say that A is not equal to B, because again, A is the set of words 1, 2, 3, so the elements are words 1, 2, 3, and B is the set of numerals 2, 1, 3. The elements are numerals here. Okay? All right, let's take a look at another example. So suppose we define A this time as in the first example. Ooh, be careful with your squiggly brackets. Those squiggly braces, they can be real messy to learn how to write. So let's define A with these numerals 1, 2, 3. Okay, and suppose we define B as the set 1, 2, 3, 4, 5. Okay, now even though all the elements in A are exactly in B, because B has these additional elements, and then we can't say that everything in B is exactly in A. So A and B don't have the exact same elements. They do have some of the same elements, but they don't have exactly the same elements. Okay, so then in this case, again, we would say A is not equal to B. Okay, now sometimes it's useful to describe how many elements are in a set, right? So not just the specific elements of the set, but also how big is the set, right? So how many elements are in a set, especially if we're talking about really big sets. This is really important. Okay, and this brings up our next definition. Okay, so when we're talking about the size of a set or the number of elements in a set, we're talking about cardinality. So our next definition is cardinality. Okay, and so we define, the cardinal number okay, again, this is what we're defining here, this cardinal number, okay, of a set is, is the number of elements in the set. Okay, the number of elements in the set. Okay, we also define this number, okay, the specific number that is the cardinal number. We call it the cardinality. Okay, so we can say that the number of elements in a set, that specific number that is the number of elements of a set, is called the cardinality. So cardinality. Okay, again, this is the word we're defining here. This is just another usage of the word, the cardinality of the set. Okay, and this is denoted in a special way. You'll see it in two different ways. So sometimes you might say, so suppose A is a set. Okay, then we might define the cardinality by using this notation. So card of A, right? So this is card of A, and this is simply read the cardinality of A. So this is, we read this as the cardinality of the set A. Okay, so that's how this is read. But you'll also see in sometimes another notation, this N of A. Okay, so N of A is the same thing. It's read exactly the same way. The cardinality of A. You might think of this as the number of elements in A. So that's why the N might, have kind of a mnemonic usage. The number of elements of A. Same thing as the cardinality of A. Okay, so that's what a cardinality of a set is. Okay, let's take a look at some examples. All right, so let's define the set D, okay, to be, let D be the set of days of the week. We did this in the previous video that we had, days of the week, right? So then the cardinality, so for the course of these videos, we'll be using the N notation, so N of D. So the cardinality of D is, of course, 7. There are 7 days of the week, so there are 7 elements in this set that is the days of the week. Okay, so that's fairly straightforward. Okay, all right. Suppose we define another set, so let A be the set 1, 2, 7, 9, pi 1/2. Okay. Again, this is a finite set, so we can count. This is fairly straightforward. So what would be the cardinality of the set? So the cardinality of A would then be, well, we count them up. 1, 2, 3, 4, 5, 6 elements. So the cardinality of A is 6. Okay, let's take a look at another example. What do you think, so a little thought experiment, what is the cardinality of the empty set? Remember, the empty set from the first video is the set that contains no elements. So the cardinality of a set with no elements is, of course, 0. So the cardinality of the empty set is 0 since it has no elements. Okay, let's take a look at another example. So the cardinality of real numbers. Okay, we won't go into the super mathematical details of this because, as it turns out, there's different types of infinity when we're talking about cardinalities. But suffice it to say, the cardinality of the real numbers, there's an infinite amount of real numbers. So the cardinality of the real numbers is infinite. Okay. All right. So again, so it's fairly straightforward. And if we're dealing with a finite set, we can actually just count the number of elements in the set. But even if we're dealing with an infinite set, or even a large set, sometimes we may not be able to count them directly, but we have to find some sort of way of counting them up or arranging them so that we can count them. Okay, so we could have finite sets, in which case the cardinality is a finite number, or we could have infinite sets, in which case the cardinality is infinite. Okay. Now, sometimes some sets may not be equal, but it's useful to be able to compare the cardinality, so compare the sizes, right? I mean, we like to be able to compare things all the time. Do you have more of this than that? Who has more money, or who has more chickens, or who has more cars, or that sort of thing? Okay, so just like with the real world, we want to be able to do this with sets. We want to be able to compare sets based on their cardinalities. Okay, and this leads to the next example and this next definition. Okay, and this is the idea of equivalence. Okay, so another definition. Building quite a portfolio of definitions in this set of videos. Okay, so definition. A set A, okay, so we're talking about a set A, is equivalent, okay, equivalent, and again, this is the word we're defining, right, so we're going to underline this. So the set A is equivalent to a set B, so another set, if the cardinality of A is equal to the cardinality of B. Okay, so we want to be careful here. Notice equivalence talks about the cardinality of the sets, not specifically the elements of the sets, but rather the number of elements within the sets. Okay, and we'll see this. Let's take a look at some examples. Okay, so let's say we define A as the set apple, orange, banana, mango, and grape. Okay, and let's say we define the set B as the set January, February, March, June, and July. Okay? Now, clearly, A and B are not equal. However, if you look at the cardinality of A, we have 1, 2, 3, 4, 5 elements. And the cardinality of B is 1, 2, 3, 4, 5 elements. So since the number of elements in A, so the cardinality of A, is equal to the number of elements in B, or the cardinality of B, then we say that A is equivalent to B. Okay? We don't necessarily have a special notation for this. There might be special notations for context. We won't necessarily use one. But if their cardinalities are equal, then we say that the sets are equivalent. Okay, not equal, but equivalent. So equivalence deals specifically with the cardinality of the set. Okay, that's going to conclude our video on equality, equivalence, and cardinality. I hope you enjoyed. Please be sure to subscribe to the channel, and we'll have many more videos coming in the future, including the continuation of this series on the introduction of sets. Please, if you have any comments or suggestions, leave them down in the comments below. And thank you for joining me. Have a wonderful math-filled day.